Hello, everyone. Just want to say you're getting very, very close to the end of the quarter, so well done. Um, just a reminder, your final will be found online on Bright Thinker. You'll need to set about an hour and a half of time. Um, so you've got loads of time to take it. You'll need a calculator. You'll need a periodic table for your final. Just be aware I will post more information as time gets closer. That's just kind of a reminder. So I want to talk a little bit about nuclear decay and nuclear chemistry. Unit 10 starts out with thermochemistry or thermal chemistry or thermodynamics, and then it kind of moves into nuclear chemistry, fission and fusion, so on and so forth. So I wanted to talk a little bit about the three different types of nuclear decay that Bright Thinker discusses. So first of all, just a little brief reminder, nuclear chemistry. So nuclear chemistry is studying the nucleus of the atom and the changes that that nucleus undergoes. So far, in first quarter, or I should say the first half of the class, and then now the second half of the class, chemistry we've been dealing with is the interaction of atoms, different atoms or similar atoms with one another. Now we are looking at the actual nucleus of an atom and the changes that undergoes. And same with why atoms combine, different atoms combine because they want to become stable. They want to have a full octet or 8 electrons in the last energy level. Most atoms are going to do whatever it takes to have a stable electron configuration and have their nucleus stable. So larger atoms, so atoms that are larger than like iron, are usually going to have a bigger nucleus. Of course, they're going to have more protons, more neutrons, and that is going to make the nucleus of the atom unstable. So nuclear chemistry is the reactions that occur inside of the atoms. And we are going to work on that today. They're nuclear reactions for nuclear decay. So far, like in the first semester, we did reactions that occur between two or more atoms. Now we're going to look at the reactions that happen inside of the nucleus. So radioactive decay, just as I'm throwing this word around, is when an unstable atom releases energy or matter, or both, from its nucleus, transforming it into a different atom. A lot of times they'll call radioactive decay transmutation because you have a certain isotope and then it breaks down or it decays, the nucleus decays, and it turns into a more stable isotope. So when we're talking about energy and matter, okay, that is being released, that is actually nuclear radiation. So anytime you hear the term nuclear radiation or radiation, it's matter and energy that's released from the nucleus of an atom. I don't know why I can't get that to go away. Anyway, so matter, we're talking protons, neutrons, electrons. Energy, we're talking gamma rays. Okay, if you remember, gamma rays are part of the electromagnetic spectrum. That's energy, that's highest energy in the electromagnetic spectrum, smallest wavelength, highest frequency. So when we talk about nuclear radiation, we're talking about matter that is leaving or changing in the nucleus and energy that's being released. Okay, so let's look at we're going to look at 3 types of radioactive decay. There's actually, I know it says 4, there's 1, 2, 3, 4, there's actually 5 types. Bright Thinker only talks about alpha, beta, and gamma decay, and so that's all that we're going to look at today. Positron emission and electron capture, those are different ways nuclei can decay, but we're not going to touch on those just because Bright Thinker does not. We don't want this to become too overwhelming. So what you are going to need for this is you absolutely positively need a periodic table of elements. You will not be able to do these problems without a periodic table of elements. You shouldn't need a calculator because it's really just simple math. Okay, so the first one is called alpha decay. So in alpha decay, you have got a parent nucleus or a atom with a very large nucleus like uranium-238. Now, just a quick reminder, this is an isotope symbol. This tells you the elemental symbol, what element it is. The 238 is the mass number, so that's the number of protons and neutrons in the nucleus of the isotope. And 92 is the atomic number. That tells you how many protons are in that nucleus. So when alpha decay occurs, okay, again, we're talking about changes in the nucleus. 2 protons and 2 neutrons leave the nucleus of the isotope. Now, these 2 protons and these 2 neutrons are actually called an alpha particle. An alpha particle looks just like this. It actually looks exactly like a helium atom. So anytime we talk about an alpha particle, and a lot of times they'll write the symbol like this, okay? Anytime we talk about an alpha particle, it looks exactly like a helium atom. It has 2 protons and it has 2 neutrons. So anytime we write these reactions, anytime we write an alpha particle, it's going to look just like this. So this is what happens to the nucleus, okay? 2 protons, 2 neutrons leave. That makes our mass number go down by 4, and our atomic number is going to decrease by 2. And by doing that, that is going to turn our parent isotope, okay, into a more stable isotope, which we call the daughter isotope. Now, if you remember, on the left-hand side of the arrow are our reactants, and the right-hand side are the products. Same thing with these nuclear equations. We have reactants and we have products. In alpha decay, we have one single reactant and it breaks down into 2 products. It breaks down into a daughter product and an alpha particle. So here it says reactant, you have one thing. It's our radioactive parent isotope. And then the product is going to produce a more stable daughter product and an alpha particle. So I'm going to show you how I like to do these equations. I think it's just easiest. I'm going to start with this guy right here, okay, 238, so uranium-238. I'm kind of don't have as much room as I thought, so I'll make a little bit of room here. Okay, so I'm going to start with my parent isotope, so uranium-238. 92. Now, I have a line here because that's the only way PowerPoint would let me do this form, but normally there isn't a line here. Okay, so I'm going to do my produces arrow. So I know for a fact that this is alpha decay, and every single nucleus that breaks down will produce an alpha particle. So I'm just going to immediately write He4 and 2. An alpha particle for sure is produced. So then the next thing, I know that my daughter product, okay, compared to my original parent, my daughter product is going to have a mass number that is 4 less than my parent, an atomic number that is going to decrease by 2. So this is what I like to do. I just like to write the numbers. So my mass number decreases by 4. So my mass number is 234. And my atomic number decreases by 2. So my new atomic number is 90. So then what I do is I go to my periodic table and I find the element that has atomic number 90. And that would be thorium. So then I'm going to add my symbol. So when uranium-238 breaks down due to alpha decay. Oh, I'm going to have to do 2 videos here. It is going to produce an alpha particle and thorium-90. This thorium-90 is going to be more stable than the original parent. Okay, so let's do my other 2 examples here. I'm going to have to probably pull this guy down and give myself a little bit more room. I don't know why I can't get rid of this guy. Oh, there we go. That's better. Okay. Okay, so let's start with Rn, which is radon. This guy is going to decay through alpha decay, so I'm just going to automatically write my arrow. It's alpha decay, so I know for sure it is going to produce an alpha particle, so He4 and 2. And now I have to figure out the daughter product. So my mass number goes down by 4. So 222 minus 4 is 218. It's Friday. I got to double check myself. 218. And my atomic number goes down by 2, so that's 84. So now I'm going to go to my periodic table and find the element that has the atomic number of 84. And that would be polonium. So radon, when it breaks down through alpha decay, will produce an alpha particle and a new daughter product, which is polonium 218. Let's do one more. Okay, so polonium 210 will also break down through radioactive decay, alpha decay. Since it's alpha decay, I know for sure it produces a alpha particle and a new daughter product. So 210 minus 4 is 206. My atomic number goes down by 2, which is 82. Now I'm going to go to my periodic table and find the element that has atomic number 82, and that would be lead. So anytime an isotope breaks down through alpha decay, it will produce an alpha particle and a new daughter product. You need your periodic table to figure out what the new daughter product is. Okay, so since my video only allows me 15 minutes, I'm going to stop there, and I'm going to talk about beta decay and gamma decay in the next video.